first one, you can use a Poisson statistic. So this yield and your area and your defect density is an exponential relationship. Okay. So if some fraction of the wafer G always produces 0 yields, then we can get rid of that part. Usually, like those strip line or the outer region of your wafers, those regions they won't produce any yield. So you can get rid of that part, so you don't count that in your yield estimation. And this model assumes that this particle they are independently randomly because that will follow these Poisson statistics. And you can also use other statistics like negative phenomenon to eliminate these assumptions, and it's more accurate. Because with these small particles, they will it's like some smaller one, they will get together to form larger ones, and larger particles they will precipitate more easily. So sometimes we can't just assume that each particle they are all randomly distributed, and sometimes they will become to form like a bigger one. So in this case, we can use this model, this statistic model to model the yield here. Okay, so we have C that accounts for these clustering factors. Okay, so again we can plot these lines here, these Poissons here, negative polynomial. If your C equals 2 or C equals 10, then which give you a more realistic case. Okay, for C equals to 2, then this chip yield, if we change your defect density, right? If this defect density is larger, then you can see the yield drop quickly as you increase your chip area. And the overall yield is the product of each the yield of each state. So we can just times them together. Okay, this I think it's quite easy to understand this. And another model we're going to do here is to model the cleaning process. Okay, and this will include some chemical reaction and some chemistries here. Okay. Okay, so in this metal cleaning can be understood in terms of the first one is to convert metal into iron and soluble in the cleaning solution, and the second one is to oxidize. Okay, and the third one this oxidation and reduction happens in this process. Okay, so for example, if you go into the right hand side, okay, that will be the oxidation process. So your silicon becomes your silicon dioxide, and you lose some electrons. Okay, and reduction is the other way. You gain electrons. Okay, so this is the metal. With metal ion, we try to remove it from our silicon. So we have to make it to. So we can combine these equations here. Okay, so there are equations 3 to 5. Okay, if you go into the right, we lose some electrons. Okay, so this is peroxide with water. Okay, so generally this equation 5 is driven to the left. Okay, driven to the left, and 3 and 4 to the right, so that we can form SiO2 and we can form this metal ion, which is soluble in your solution. Okay? So that's where we'll try to combine these three. Okay. So here are some potentials we listed in this table with different those oxidant we showed here. Okay. So this is the reductant or the oxidant we showed here, and this is standard oxidation potential. And on the right column is this is chemical reaction. Okay. The strongest oxidant are listed at the bottom of this table. Okay. And these reactions will go to the lab and grabbing electrons and dominating, and to force. If you have strong oxidant, right, you will go to the left, and which will reduce these electrons. It makes equation 3 and 4, because you have electron go smaller and you will go to the right. So that's why we're trying to find this H2O2 here. We have to add H2O2 in our solution. Okay? Or even you have the stronger one is this ozone here. Okay. Now we're trying to model the gathering process. Remember, there are 3 steps. The first one is to free these metal atoms to make it mobile. The second one is to make them diffuse to the trapping sites. And the third one is to trap these atoms. Okay, so the step 1, we can kick out these atoms from their substitutional site and make it into interstitials. Okay, so this is one possible reaction we have. Okay, this is a substitutional gold, and if we have another interstitial silicon, right, we combine them, they will switch position. Now you make this gold become the interstitial site, and they can move around, begin to move around, right? So that's the possible reaction we have first. So we need to have this I that plays an important role in this process, in the first stage. Okay. Okay. So the step 2, right? Those metal that are in the interstitial side, they begin to move around through the diffusion process. So this happens quickly if you increase the temperature, then they will move around. Okay, and the third one, once they segregate together to form in this damage or in this trap size. Okay, and then they will pair with some other effective gators like phosphorus become these AUP pairs. Okay. Okay, so let's take a look at these figures. The first step is we can free these metals from their substitutional site, and then second, they begin to diffuse to this intrinsic gathering region or the extrinsic gathering regions, and then become trapped here. Okay, so once the metal in interstitial sites, their diffusion constant is 10 times larger, become 10 times larger, so they can move around. Except for titanium or molybdenum, they are primarily preferring the substitutional site. Okay. And also from the previous these figures that we just showed here, okay, these figures is quite important because you can see these metals and all the I defect, they all move faster than your conventional dopant here. Okay. So they can quickly move to the trapped site. Okay, those trapping sites, they will get this metal quickly. Okay. Okay, so okay. So you want to free this gold. You have to add some I here. Then you can. This is called a kick-out mechanism. So you can kick this gold out of the substitutional site. And if your I you have V, okay, they will go back to substitutional site. Okay, so we need I to increase or to improve this gathering process, and V will do the other way to hinder the gathering process. Okay. And remember the previous figures show that the silicon interstitial actually move faster than the dopant, right? But they still significantly slower than the metal atoms. Right? The previous page we just showed that. So which one will be the dominant process in this scattering? Okay, in this scattering process, the smallest part, the smallest one, will be the bottleneck of this process. Okay, so which will be what? Will be your I, right? Because I is moving slower than your metal, and you need once you have I reach to the metal side, then you begin to free this metal, and the metal will quickly go through the trapping sides. So the bottleneck will be the slower one, which is the I diffusion, the interstitial diffusion. Okay. Okay, so on the left-hand side, this figure shows you the gold concentrations, and it's a function of your depth. Okay, so this is the backside trap. So once your metal reach to your backside, then you'll be trapped. So your concentration is smallest at here. Okay. So as time increased, you can see this gathering process begin to help you to reduce your gold concentration inside your material. So you're starting with like a more flat profile, like 10 to the 15. And then this concentration drops with your time. Okay, it's to the wafer as the gold diffused to here, to this backside here. Okay, so if you notice this time. right hand side here is this, you do the experiment at 1000 degrees C, and you see this gold out diffusion profile during this gathering process. Okay. So again, if we increase this time, this is right. This is simulation, and this is the experimental data. So this is originally the profile, and then you increase from 5 minutes to like 60 minutes. We can see this at this backside, the gold concentration will drop quickly, right? And the dominant reason for this profile actually is is how far the silicon interstitials have diffused heat from the backside, because we create this some roughness on the backside, so that will generate a lot of I. So the I will move to here at a certain time, then begin to free this metal, and once the metal becomes the interstitial metal, they will diffuse to this trapping site very fast. Okay, so it can easy for us to understand that this metal profile actually is determined by your interstitial profile, that how fast can it move, can it go. So if you increase this time, actually just to have your eye to move deeper inside your bulk material. Okay. Okay, and then the third step is to trap the metal ion in this scattering site. Okay. Okay, so during this either implantation or diffusion or some damage process, will create some physical damage. Okay. And this physical damage can trap this metal, and we can use this binding energy EB to describe this this process. It's like a trap, right? So once you have metal get into the trap, then it's no way to get out from this trap. So here's the exponential term here. This EB, this binding energy, also you can consider like an activation energy. Okay. So it's like exponential term here, and okay, and also there's also exists a segregation coefficient, okay, between the gold in the perfect crystal and in the gathering region. Okay, so this concentration will be different because you have different these parameters and also the activation energy here. So once you have this segregation, this concentration difference, then we can define the segregation coefficient as the one that total concentration of gold, okay, and also compared with the concentration in your perfect crystal. Okay, so if you write this, your segregation coefficient can be written like this equation. Okay, so we can consider the case for phosphorus, then we can have this equation. Okay, so we don't need to memorize this kind of equation, but we try to get some physical idea from this and to understand what's really going on here. Okay. So once you increase your dopant, you increase your Ng, which means you have more trapping size or defect size in your materials, and that will increase your segregation coefficient, which means you get a better gantry process. Or you can reduce the temperature. Here, they can also give you a better gantry. Okay. And we can also use this chemical reaction to model those gathering process. Okay. So we can write this. There's a constant chemical reaction constant. Okay, we can use the concentration of this Au minus divided by Au times the electron. Okay, it's either for intrinsic or for doped material. You can write this chemical reaction constant. Okay, so now if we plug the intrinsic or the N-type or the P-type in this equation, for example here for the intrinsic and N-type, then because the K is this K is a constant, right? So this concentration difference will be reduced to your dopant or your electron concentration difference. Okay. So once you increase this N-type your silicon, then this we're getting close to your doping level, especially at high temperature. Is Ni. Okay, and so that's one way we can model the third state of the gathering process. How can this metal can be trapped in this trapping state? Okay, and we can use this ion pairing model because once they form this pair, they can give you less strength. So they prefer in this kind of compound form, okay? Or we can use some Coulombic attraction to describe this phenomenon that, okay, they have some Coulomb attraction, Coulomb force between them. So they can form this kind of gold and phosphorus compound. And also we can introduce this point defect V in this N-type material. Okay, and also we can introduce the I in this process. Okay, here during the intrinsic gathering, right, you have you created the compressive or tensile stress. So you have, because you change from silicon to SiO2, and you introduce some stress here. Okay. Okay. So again, this is quite difficult that people propose that different model and different models and different physics try to explain what we observed during the experiment. So sometimes it's very complicated. So it's not the main purpose of this class. So we just give you a brief introduction of how can we model this gathering process. Okay, and here are some limits and future trends in technology and modeling. How can we eliminate the defects from our wafers? Okay, those defects can be your particles, contaminants, okay, or we can give a more cleaner environment to IC fabrication. And we can use this standard mechanical interface. Okay, this box. We can also it's more smaller size to you can put wafers inside and transport them between stations. Okay, and also wafer cleaning is the next slide. Gathering, intrinsic and less extrinsic. Okay, when we can do the growth, we can control the O and oxygen and carbon, and use low temperature processing because that will create less defects. Okay. Okay. So this is the cleaning process that we have seen this. But in the future, we can use ozone. Okay, copper ozone in this cleaning process. We can use dry and vapor phase environment. Okay, we can use some low energy physical process like sputtering. Can help you to remove some maybe lead oxide or some iron on the surface of the wafers. Okay, and also some photochemical enhanced clean, which means when you do this chemical reaction, you will shine a light, maybe some light with larger energy, like a UV light, can help you to enhance your cleaning process. Okay, so here just to summarize what we have learned in these chapters. Okay, the first one is that we have three-tiered approach to control the contaminations from the clean room, from those wafer cleaning process, and also the gathering process. Okay, and we can use this particle control, wafer cleaning, and gathering, some of the nuts and bolts of chip manufacturing. Okay, so you have to it's very important that you have to tweak it a little bit, and also people starting different ways to control this process. And there's economic issues, especially that you have high yield of your chip, you can sell it, you can make more revenues. So that yield is very important to drive this cleaning process. Okay. There's level 1, 2, 3 control that I just mentioned. Okay, and the bottom line is the chip yield, right? So we need to make money by making good dies. Okay, so that's the end of these chapters, and we can continue to move on.